Hi, today I'll be presenting our work titled Improving Name Entity Recognition in Spoken Dialogue Systems by Context and Speech Pattern Modeling. In this work, we explore the task of identifying name entities in spoken dialogues between humans and chatbots. Name entities can be hard to identify in dialogues because dialogue utterances may be ambiguous, especially when taken out of context. Besides, transcripts of dialogue utterances from automatic speech recognition system may contain many errors. Furthermore, transcripts may lack consistent letter casing and punctuation, two features that are important for name entity recognition. The presence of disfluencies and repetitions also poses additional challenges to this task of name entity recognition. In this particular example, without additional information, it is unclear whether there's any name entity in the user utterance. However, when the previous utterance is known, we are more certain that the user probably mentioned a book name. However, that is still not clear where precisely in the user utterance is the book name. If we also know that the user paused briefly before saying the phrase "the notebook," then finding the book name is easier. So the intuition behind this is that context will help determining the entity type, whereas speech pattern features will help determining the entity's location. We propose an approach to exploit dialogue context and speech pattern features for identifying name entities in spoken dialogue systems. First, the dialogue context is encoded into a single context vector using a backup embedding model with max pooling. Next, the lexical representation of every tokens in the user utterance is encoded using word embeddings and characters embeddings. Then, the speech pattern features are encoded using a bidirectional long short-term memory. The speech pattern features are pauses, word duration, and tokens ASR confidence. Pauses could signal boundaries between grammatical structure within utterances. Therefore, pauses can act as punctuation in dialogue utterances. Since punctuation are not available in ASR transcripts, this can be very useful. Exaggerated variation in word durations and pauses could be present when pronouncing non-native names. And token confidence might also predict the presence of name entities, since name entities appear less often than other words. Therefore, these 3 or 4 speech pattern features may be useful for name entity recognition. And finally, we combine the context and lexical and speech pattern representation to predict the token text. The lexical and contextual representation are combined using element-wise addition, whereas the speech pattern features are combined using a linear layer after concatenation. So now, here is the data that we use in our experiments. The data are from conversations between humans and the Dialog chatbot. The Dialog chatbot participated in the 2019 Amazon Alexa Prize. Each data sample consists of one chatbot utterance and the following human utterance. Chatbot utterances are in mixed case, while human utterances output from an automatic system, a speech recognition system. Therefore, they are in lowercase. The data statistics of the data set are shown in the right. Um, the data are divided into two different splits, namely a standard split and a hard split. The standard split and the hard split share the same training sets. However, the development sets and the test sets of the hard split are created such that they have more named entities that are not seen in the training set. The overlap of named entities between the training sets and the test sets is measured using vocabulary transfer. The development and test sets of the hard split have much lower vocabulary transfer than that of the standard split. This can be seen in the table at the bottom right. The test sets of the hard splits more closely resembles the data during the chatbot deployment. This is because this is very common to encounter new names during deployment. Thus, a high performance on the hard split is a realistic reflection of the model robustness during deployment. The data are labeled using 6 different categories. The categories are movie, book, song, person, character, and other. And so this is our experiment result. Modeling context consistently leads to significant gains in F1 score, regardless of the data split or the model structure. So in both standard split and hard split, both the bidirectional LSTM model and the BERT model performs better when context is given. Adding speech pattern features did not lead to notable changes in F1 score when testing on the standard split. However, when testing on the hard split, the gap between using and not using speech patterns features is more noticeable. This is perhaps unsurprising, since the number of shared name entities between the standard split, training, and test sets is quite high. So exploiting complementary features like speech patterns may be less beneficial. In all setups, combining speech patterns feature with context resulted in the highest F1 scores. So we know that speech pattern features are useful, but are all the features useful? In order to determine the usefulness of the different speech pattern features, we conducted ablation study by removing the features one by one. We trained all the models with ablated features from scratch, including hyperparameter search. For the hard split, the BERT4F model did better than the BERT3F model, showing that ASR, or automatic speech recognition confidence, is probably useful since low ASR confidence can indicate names which appear infrequently. Similarly, the BERT3F model did better than the BERT2F model, suggesting that the token duration is probably also useful. Next, we look at some prediction made by the models and found that the models behave as expected. For this first example, Lord of the Rings should be classified as a movie. However, without context, both the bidirectional LSTM model and the BERT model predicted the text span as a book, which is the wrong entity type. Similarly, in this second example, the notebook should be classified as a movie. And without context, um, the bidirectional SDN couldn't even find the name entity in this user utterance. Um, this is understandable because the utterance can be ambiguous without context. Um, the BERT model, on the other hand, managed to predict the correct text spans. However, um, it got the entity type wrong. So um, um, while dialog context helps identifying the correct identity type, speech pattern features may help locating the name entities. So in the third example, McLovin should be predicted as a character in movie. We can see that the ASR token confidence is very low for the McLovin token, indicating that this is probably a rare token or probably a rare name. Um, so without the speech pattern features, the LSTM model predicted the wrong text span and also the wrong type. With speech pattern features, um, the models managed to predict the correct span. However, the types are still incorrect. This suggests that additional knowledge may be beneficial for this task. Um, so in summary, both context and speech patterns are useful for name entity recognition in dialogues. Um, in particular, context is useful for identifying entity type, while speech patterns is useful for identifying entity position. Um, for more details, please check out our paper. Thanks.